Okay, now, almost everything that we're using in shows today has a computer in it. And a lot of them now will have the ability to get on a network. But they're basically computers. So the way digital electronics work, the way computers work, the way anything that has a computer chip in it works, is that it uses binary numbers to manipulate data. And so binary can be easily, the reason they use binary numbers is because you can very easily represent binary numbers using voltages and switches. And the low voltage DC comes from the power supply in the fixture. When you plug in a fixture, there's a power supply that takes the AC power from the wall and converts it to low voltage DC. And then their integrated circuit chips have millions and millions of transistors in them that can switch the voltage on and off. Now, when I was a kid, a transistor was an amplifier. And then at some point, they became switches. And I'm like, wow, I never got that memo. I didn't know that happened. But that's the way we use transistors now. They're switches. And so if I can switch the low voltage on and off, I can generate binary numbers. And so therefore, when we went from analog to digital, the control signals that we're using used to be variable voltage. Now they are square waves. There's either voltage or there's not. So that's a square wave, right? So the way it works is that voltages are used to represent binary numbers. And in binary, there's only two digits. There's 0 and 1. That's it. So if there's no voltage, that represents a binary 0. If there's voltage, that represents a binary 1. And just with those two digits, they're grouped together. They can either represent an operation, like add, subtract, multiply, divide, logical and, logical or they can represent data like numbers, like the value, DMX value. And if you think about it, everything we do with computers, moving yokes, painting screens, painting monitors, doing calculations, doing renderings, doing VR, that's all done with those 6 operations: add, subtract, divide, multiply, logical and, logical or. It's mind-blowing to think of the power of those 6 operations, but that's all they do. So if I take a power supply and I switch it on and off, then I can transmit binary numbers. So for example, suppose I had a 9-volt battery and a switch and a pair of wires. And if I ran those wires to the back of the room where Ray is, and I gave Ray a voltmeter, then I would tell Ray, every time there's voltage on the meter, write down a binary 1. Every time there's no voltage, write down a binary 0. And in that way, I can turn the switch on and off, and I can transmit data to the back of the room where Ray is. And that's an example of serial data transmission, because it's one bit after another in series. If I had 8 batteries, 8 switches, 8 pairs of wires, and I gave Ray 8 voltmeters, then I could set the switches and I could transmit 8 bits at once. That's parallel transmission. And back in the 80s and 90s, we used there were parallel printers with parallel cables, and we don't use those anymore. Today, almost everything we do is serial data transmission. If you look on your computer, your USB port, that's a serial data port. And in fact, that's the same interface that we use for DMX. And it's similar to what we use for everything else as well. Now notice also when I do this, when I'm switching the voltage on and off, it's generating a square wave. So a square wave is a digital control signal, or a digital control signal is a square wave. We grew up, humans use the decimal numbering system. In decimal, there are 10 digits, 0 through 9. And we arrange these digits in columns according to how much, according to their weights. And then we add them up to convert them to a number. So in binary, there's only 2 digits, 0 and 1. If I had a switch like this represents a dip switch. You've seen those tiny little dip switches on some older fixtures and fog machines and smoke machines. With the switch, I can represent binary numbers. If the switch is off, that means binary 0. If I turn the switch on, that's a binary 1. So with one switch, I can count to 1. If I wanted to count higher than 1, I would have to add a second switch. And if this switch was off and that switch was on, that would represent the decimal number 2. Or if they were both on, that would represent the decimal number 3. Now to count higher than 3, I could add a third switch, and then this one's off, that one's off, that one's on. That means 4. And then if I turn this one on, that one off, that one on, that's decimal 5, and so on. And I could keep adding switches, and then I could count as high as I wanted to go. So in this scheme, you might notice that every time this switch is on, you add a 1. Every time this switch is on, you add a 2. Every time this switch is on, you add a 4. Every time this switch is on, you add an 8. And then the next one would be what? 16 and 32 and 64, 128, 256, and then, so do those numbers sound familiar to you? Those are all powers of 2. Powers of 2. So you'll see those a lot with digital electronics. So this would be the 1's column, the 2's column, the 4's column, and the 8's column, right? And these are all powers of 2. The next one would be 512, 1024, and so on, right? So if I wanted to convert a binary number to decimal, I could look in the column, and if there's a 1 there, then I would add that power of 2. So in this case, this binary number, which is 1110101, converts to the decimal number 117. Okay? Now, hexadecimal is going to be more important in the future. Why? Because our IP addresses soon will be hexadecimal numbers. Right now, we're using version 4 IP addressing. You might have noticed that when I had you change your IP address, I had you look up that line that said Internet Protocol version 4 and click on it and go into the properties to change the IP address. But there was another one that says IP version 6. IP version 6 is what the world is converting to, and IP version 6 is hexadecimal numbers. Hexadecimal is base 16, and in hexadecimal there are 16 digits, 0 through 9 plus A through F. And with those 16 digits, you can count and you can convert back and forth between decimal and count to any number. So in the hexadecimal numbering system, every column is a power of 16. So you could convert, for example, the hexadecimal number 23B, that would convert to decimal 571. Okay, so in binary, if you wanted to count in decimal, you'd start with 1, and then binary 10 is equal to decimal 2, binary 11 is 3, and then 100 is 4, 101 is 5, 110 is 6, and 111 is 7, and so on. Okay? Now, the next little slide in your worksheet, it asks you to write down the binary numbers from 1 to 20. I'll let you do that on your own. All right? So if you want to try that, and I'll give you a hint too. If you have a computer, if you call up your calculator, so if you look up here under View, normally you're in scientific mode, but there's also up here in View, there's a program mode or programmer mode. And in programmer mode, you can convert back and forth between binary and either decimal or hexadecimal. So right now this is decimal. So I could type in a decimal number like 56, and it'll tell me the binary equivalent, which is 111000. So if you wanted to use that, and in the future you may need to when you're setting your hexadecimal number IP address, that might come in handy because you also have the option to convert it to hexadecimal. Now you might notice that, I don't know if you can see it in the back, but up here this number says 0x38. Anytime you see the number that starts with 0x, that means it's a hexadecimal number. So this is not the number 38 in decimal. That's not what that means. In decimal, that's actually 56. It's a hexadecimal 38, which is different than decimal 38. Okay? Now, the way computers work is that they will organize bits of data in groups of 8. 8 bits is called a byte, a B-Y-T-E. And half of a byte is called a nibble. And I didn't make that up, that's true. Half a byte is a nibble. And the reason a nibble is important is because one nibble converts neatly into one hexadecimal number. And especially if you're writing code. And you know what? More and more, I'm running into people in our industry who are learning to code. Why? Because there's all kinds of interfaces like OSC, and you know, if you know how to write in Python or in you know, some other languages that are used to create your own interface. Now you can lay out your own tablet and your own buttons, and you can make them do different things by interfacing with the console. So now instead of being stuck behind the console, you can walk around with the tablet and you can trigger cues and do that kind of stuff. So there's a growing demand for coders in our industry. But now, with 8 bits of data, remember 8 bits is a byte. With 8 bits, there are 256 different levels, or 256 different combinations of 8 bits. So DMX, for example, is an 8-bit protocol. That means that every byte of data, you can represent 256 different levels, whether that's a dimming level, whether it's pan or tilt. You can divide it 256 different ways. In some instances, that's plenty. That's plenty of granularity of control. So for example, if you're trying to dial in a color wheel with 8 colors plus open, that's only 9 slots. Then 256 divided by 9, you know, that's plenty of control. On the other hand, most moving lights will pan 540 degrees. So if you have 540 degrees of pan, but you only have 256 levels of control, that's not nearly enough because the steps are going to be too big. So the movement will not be very smooth, it's going to be very steppy. So therefore, some parameters we will use 2 bytes of data to control, like pan. And so the 1 byte will be the coarse control, and the other encoder, or the other value, will be the fine control. So that means that you have 256 levels between every step of 256, which now that gives you 65,000 steps of control. It's much more smooth movement. It's much more accurate. So if you're trying to throw 40 feet to downstage center with 256 steps of control, you might be able to target to the left or to the right of downstage center, but not exactly downstage center. But with 2 bytes, or with high resolution 16-bit control, now you have amazing accuracy and you can dial it in exactly where you need to go. So now there are a growing number of protocols in our industry. There's new protocols being developed all the time. Some are industry standard protocols, some are proprietary, and some are open protocols. The difference is that in an industry standard protocol like DMX and RDM or streaming ACN, those are consensus protocols. They're developed by committee from volunteers with volunteers in the industry, and it goes through a rigorous process whereby the industry, they develop a consensus within the industry that that's how we want this protocol to work. The advantage is those become interoperable, so it doesn't matter what gear you're using. Whether it's an M series, whether it's a grandma, whether it's a hog console, DMX is DMX, and it should work exactly the same. That's an interoperable protocol. On the other hand, sometimes they take a long time to develop because of the process they have to go through to develop them. So it's quicker and easier if a company decides they need to develop a protocol. If they develop a proprietary protocol, they can do it any way they want. They don't need anybody's permission. They don't need anybody's agreement or consensus. They can just develop it and put it out there. So that's an example of ClingNet, KaiNet. Those are proprietary protocols. ETCNet, StrandNet. Those are all proprietary protocols that they can develop very quickly for their own purposes. And then there are open protocols like ArtNet and CITP. CITP is a way of streaming thumbnails of media server files to a console so that instead of having a file name or number, you actually get to see what the media looks like before you select it and put it up on the screen. So that's a very handy thing to have. So there's different types of protocols for different applications, different purposes. The baud rate is the rate of data transmission. The baud rate for DMX is 250,000 bits per second. 250,000 bits per second. That's, again, by today's standard. We talked about this yesterday, but by today's standards, that's very, very slow. But it works, and it does exactly what we need it to do. And so we still use it today. And we talked about how reliable DMX is and how bulletproof DMX is. And if there's one thing in this industry that we really value, that's reliability and dependability. When you hit the go button, it better go. So that's why we're still using DMX. Now, when you build a network, like we just did, what you guys learned or found out, or maybe you already knew, is that sometimes the network can slow things down. So there might be a difference between the baud rate, the rate at which data is coming out of a console, and the throughput, which is the amount of data that actually gets through the network. The throughput is what we're concerned with because that's what's actually getting to the actual devices. And the throughput depends on the network. And the speed of the network depends very much on the components of the network. It's going to depend on the switch. It's going to depend on the type of cable we have. It's going to depend on the network interface card in the console. Sometimes when you look at the Ethernet port on the back of a console or a light, it'll tell you the speed of that network interface card. Sometimes it'll say 10/100 base T or base TX, or sometimes you have to go to the specifications for that piece of hardware to find out the bandwidth or the speed of that component. So for example, this is a gigabit switch. So if I were to look at the specs, it would tell me the speed of that switch is 1,000 megabits per second. So, and remember, a network is only as fast as the slowest component. If I spend money to buy a gigabit switch, but then I use Cat5 cable, or if my network interface card is only a 10 base T or 100 base T, then that's a bottleneck. And I'll never get gigabit speeds because I've got a 100 megabit or a 10 megabit network interface card. So if you want the best speed, you have to think about the entire network and think about what kind of throughput you're getting. And the throughput also depends on the amount of traffic. So the more fixtures you have, the more devices you have connected to the network, the more traffic there is, the less responsive, the less throughput you have on the network. And that's why we're concerned with things like casting. Are we broadcasting? Are we multicasting? Or are we unicasting? Now, we don't just throw the data out on the network in a continual stream of data. What happens is the console will generate some data, and they'll put it in a packet, send it out across the network, and then the receiver gets it and takes the data out of the packet and uses it. So this is what we call a packet-switched network. So all the networks that we're using are packet-switched networks. DMX is a packetized protocol. You know, one packet of DMX has 513 8-bit bytes of data. The first one is the start code, and then the next 512 are control channels. Ethernet has a different scheme, a different packetizing scheme, but Ethernet is a packet-switched protocol as well. And one packet is 1,518 bytes of data. Now here's what we call a riser diagram for a typical show. This is actually a larger show, but nevertheless, it gives you an idea of what a riser diagram looks like. So a riser diagram shows you the layout of the racks and all the components in the rack. So if you're going to put a show together, a big show, and you want to assemble the racks, you'll look at the riser diagram, go to the shop, pull all the gear, and put it in this order. And then it also shows you a signal flow for the data as well. So I don't know how well you can see this, but what we have is a main console and a backup console, which is very common, very important these days, because again, a console is just a computer, and computers can crash. So if you have most modern consoles today, when you configure them properly on the same Ethernet network, they will track each other. And so you can set one as master, one as the backup, and every time you record your show, it'll save your show to the main hard drive and the backup hard drive. So now you have a copy of your file. But remember, good backup practices, I recommend 3 copies of your show file on 2 different forms of media, one of which is stored off-site. So if you only have 2 copies of your media, what happens if the building burns down? You've lost your entire show. If you're a programmer, that's your bank right there, right? So you have to protect your career, you have to protect your data, and the best way to protect it is to have good backup practices. So in addition to saving your show file to both consoles, you should save it to a thumb drive and store one of those thumb drives, take it home every day. Put it away, put it in a good place. Or, we talked about this yesterday, but if you save it to the cloud, just make sure that it doesn't compress it beyond recognition. So if you save it up to the cloud, then download it from the cloud and load it on your console and make sure it works. If you find that it works, then you can trust it. Otherwise, there's no guarantees. So in this scheme, the output of the consoles goes to the the NPUs, the network processor units, and those output to a switch, just like that switch. In this case, the switch has fiber ports, so we're converting from copper to fiber. And the reason we want to convert to fiber is because fiber gives us, there's a lot of bandwidth, and it gives us much more transmission distance. So you can go very, very far with fiber optic cable. Of course, we talked about the advantages and disadvantages. We'll talk more about them, but fiber can be expensive, it's fragile, it can break, but you do have that option. And then we've got a switch in every corner of the stadium, and then they've closed the loop. So that's allowed sometimes, but you have to have a special switch that allows you to close the loop. Now, here's what a packet looks like. A packet will have some header information, and that's for housekeeping. And usually in the header, it will at least have the destination address, where's the data going, and it might also have what kind of data is in the packet. Is it DMX data, is it RDM data, or is it something else? And then the actual data itself is called the payload. Now, this is a video that it's actually made by ETC, but it's just an introduction to networks. And when I saw this, I thought, oh, that's a great primer video. And so I called up David Fox at ETC and asked him if I could use it. And he said yes, of course, because it's got the ETC branding all over it, right? But I think it's a very good primer, as a starting point for talking about how Ethernet networks work. So I'm going to get the sound connected over here, because I forgot to do that, and play this. It's just a relatively short video.
And that pretty much concludes the tour of our lighting network. Not nearly as confusing as you thought it would be, right? Any questions?
About 1,000. But I know you don't have time for them all. Yeah, I really appreciate you going through all this networking stuff with me. I know I should have learned it sooner, but when I've got smart students like you, it's just too easy to let you run with it.
That's okay, Roy. I had fun doing it.
Oh, it's too bad you're graduating. Oh, you know what I mean.
Well, it gives you a good reason to finally learn it. Now, do you think you've got all this well enough? Or should I enroll in another semester?
No, I'll be fine. Get out of here. Thanks again. I'll see you at graduation.
Don't sweat this stuff, Teach. You're a smart guy. You'll figure it out.
Uh-oh. What's the matter there, Teach?
Feeling old, bobblehead Fred. Feeling old.
Another graduating class got you down.
Well, sure. That's always bittersweet, but it's also all of this.
What?
All this networking stuff. I'll admit I should have learned it years ago, but you know how production schedules are. I had students who ate this network stuff up, so it was easier to leave it in their hands while I was busy teaching, building, inventorying. Now I feel like lighting has passed me by.
Nonsense.
No, really. 10 years ago, I plugged a cable into my console and the wall, and it worked. Lights on, lights off. Now, I've got nodes and switches and net taps and Cat5 and servers and backups and a whole bunch of acronyms I don't even understand. I mean, do I even need all this stuff?
Need? Well, I don't know if a lighting network is a necessity, but it sure can help by letting you do complex things much more easily than you can without it, and some things you can't do at all. In fact, I'm sure you've already seen its benefits in action, and there are plenty of them.
All right. Refresh me.
Glad to. For one, networking gives you more flexibility. In a network system, you can easily use multiple control sources from numerous locations, run by several different programmers all at once. Your tech rehearsals go a lot faster when you've got two programmers building your cues at once, don't they?
Yeah, they really do. It saves us a lot of time. And the shows look better, too. One board op concentrates on moving lights and the other on conventionals.
That's right. And you've hit on another great network benefit, expanding your control capability. The network boosts the number of addresses available to you exponentially. Well, that gives you room for all of your LEDs, movers, and other devices that can eat up a single DMX universe in no time. Well, on top of that, the network makes it possible to have a backup for your console, ensuring redundancy of your control source during shows. And it also lets you receive device feedback like RDM, which helps you manage all the technology we now regularly use in lighting.
BF, that's part of the problem. It used to be the console talked to the dimmers. Bam! Simple. Now I've got all this network gear piling up in my booth, on the grid, on my tech table. I mean, how does it all even go together?
Okay, let's bridge that gap. We'll start with your simple DMX system. Now, like you said, a console communicated to the dimmers and lights came on.
Check.
Now your console and your dimmers don't connect straight to each other, they connect to the network. And we can connect other devices to it as well.
Like what sort of other devices?
Well, like another console, for instance. Or the remote processor you have as a backup. Or the video interface that lets your designer watch levels down at the tech table. Not to mention your gateways, which deliver data to all of your LEDs and movers. Well, you can see right there how much more capability you have thanks to the network.
Sure, I see it. And it's true. The network has been a real benefit for my designers. The shows have been looking great. But what about reliability? Everyone knows how finicky networks can be. I mean, isn't there a risk to trusting my lights to the flaws of networking?
Not really. Networking has come very far in terms of reliability. The technology itself is more robust and has long been reliable enough for many industries, from banking to sound production.
Well, part of my wariness is the whole troubleshooting thing. I mean, when something goes wrong, I don't have a clue how to fix it. With DMX, my problems could always be solved with hardware. Termination was off, a wrong address, a broken cable. With the network, I don't even know where to start.
I find your lack of faith disturbing.
What?
Sure, a lighting network is different from DMX, but the similarities can serve as your starting point.
All right, Shorty, show me.
In your DMX system, the console called out data to your dimmers and other devices in one big pipeline. All the data got reported to all the devices. Every device had a unique address, so it knew what data to react to, right?
That's right. Easy to map.
Well, networking isn't that much different. The primary difference is that rather than having one direct line of data transmission that everything listens to, a network is arranged in a star pattern, centered around a network switch. All of your devices connect to the network through that switch, or through multiple switches. Now, with all that communication happening, each device needs to know which data is meant for them. So they all need a unique identifier on the network. A name, so to speak.
Kind of like an address?
Exactly like an address. Well, in fact, the name is referred to as an Internet Protocol, or IP address.
Of course. I've heard of an IP address before. But what is it exactly?
An IP address is a series of numbers broken up into 4 parts called octets and separated by periods. The numbers used in these octets establishes the scope of a given network and the devices that are on it. Every device on that network has to have one so it can be identified, and no 2 devices can have the same one. If they do, communication problems can occur.
You said the numbers in the IP address establish the scope of the network. What do you mean?
Without getting too deep into detail, devices that have the same numbers at the start of their IP address typically will operate on a single network. For example, all these devices start with 10.101, which in this system places them on the same network.
So how do I know what a device's IP address is? And how do I change it if I want to?
Typically, the IP address can be found in the settings for the device. Lighting consoles, dimmer racks, gateways, remote processors, all network lighting gear has settings dedicated to networking. Usually you can find and change the IP address there.
Man, when you rattled off all that stuff, I realized just how many IP addresses I'll be dealing with. It's going to be a lot of work keeping track of all of them and making sure they're all right.
The good news is you don't have to.
I don't?
No. Network engineers have designed methods to automatically assign IP addresses and make them compatible with a network.
Fantastic! How can I make my system do that?
Since there's no way to know what IP addresses will work on all networks all the time, when new devices are connected to a network switch, their defaults would make it impossible for any of them to function.
That looks really bad.
Yeah, it is. So, a protocol was created to establish that when new devices appear on a network, they essentially ask for an IP address. They send a call out saying, "I don't have an IP address. Can anyone give me one?" So this is called Dynamic Host Configuration Protocol, or DHCP.
Ask for an IP address? Who do they ask?
Great question. Essentially, they ask the whole network, hoping that one of the other devices out there can answer.
So who can do that?
Some devices can be set to be a DHCP server, that is, a device that is able to hand out IP addresses for their network. Lighting consoles, computers running network configuration software, and lots of other devices can be set to be DHCP servers. And once they receive the call, they send out an address to all those devices so they can start communicating.
That's awesome.
And it saves you a lot of time.
Okay, but what if 2 of my devices are both set to be DHCP servers, like my console and my backup processor? Won't they both try to answer a request?
Now you're thinking like a network specialist. If 2 servers try to operate on the same network, problems can arise when new devices come online. Both will get the request, both will send an address, but the device will only accept one. So when the other server tries to communicate with the device, it won't be able to because it will be sending data to the wrong IP address.
I knew it.
So for the average user, it's best that only one device is set to be a DHCP server on any given network. That way your gear won't be stuck between 2 servers.
How do I pick which device should be a server?
Well, that's up to you. But you may want it to be the one piece of equipment that is sure to always be on the network, like your primary console. Or leave it up to a dedicated network configuration device. At ETC, we've developed a network configuration tool, Conductor, whose sole purpose is to manage all of the devices and their addresses and data on your lighting network.
Sounds like I need that. It'll help me keep all this gear straight.
So will some review. Remember, when it comes to networking, first consider the benefits. A lighting network facilitates multiple control sources, allows for two-way communication, and it expands your lighting capabilities with more addresses.
And I can vouch for all those things.
And to help demystify the process of networking, we also identified what an IP address is, mentioned where to find and change it in your device's network settings,
And we talked about how IP addresses can be assigned from a DHCP server, so I don't have to keep them all straight.
I gotta say, you're doing a lot better than you were a few minutes ago.
Yeah, I guess I am. Once you break it down, I guess it's really not as confusing as I thought.
And you've got a better grasp of all the ways networking has helped your team, your designs, and your productions.
Thanks for taking the time to explain all this to me, Bobblehead Fred. Say, since you're here, it's the end of the year. Time to clean all my Source 4 lens tubes. Want to stick around and help?
All right, so hopefully by now, by talking about it and doing our little exercises, you're getting an idea of how networks work. Now, the way networks were designed, and it's really pretty clever, is that, because if you think about, wow, how can you send an email from here around the world and get a reply back? Well, networks are divided into different tasks, right? So the standard model is called the OSI model, and it's really 7 different layers of software that work together to make a network work. And the first layer is called the physical layer, and that is all the hardware, all the things you can touch, the network interface cards, the cables, the connectors, anything you can touch is part of the physical layer. And it's also what is physically generating the voltages that are being transmitted across the network. It's what's actually generating the bits. The next layer is called the data link layer, and that's the layer responsible for the physical addressing and the framing of the data. So the physical address is the MAC address, and again, it's kind of like an electronic serial number. The next layer is called the network layer, and it figures out the best path to get your data from point A to point B, because in a big network, there may be many different paths for the same data. So it's going to try to find the best, fastest path to get your data across the network. And it also deals with the logical addressing, the software address, or the Internet Protocol address, or IP address. So that way it delivers it to the right destination. The rest of the layers you and I do not deal with too much, with the possible exception of the presentation layer, which involves encryption and decryption, which one day I think will become a bigger and bigger issue in our industry. Now, the physical layer, again, includes the topology. How are we connecting everything together? Ethernet is a star topology. That means you have to send one cable to every device on the network. Now, when you have a switch, of course, now you start the star over again. So some fixtures have built-in switches, so that allows you to build a topology that doesn't quite look like Ethernet, because you can daisy chain the Ethernet cables. DMX, of course, is a bus topology. So that allows you to daisy chain the cables up to 32 devices. The physical layer also the physical layer will also determine the speed of operation of the network, because again, the network is only as fast as the slowest component on the network. So if you look on the back of some consoles or some devices, if you look at the Ethernet connector, this is the network. This is connected to the network interface card, and the network interface card has electronics on it that are limited in the amount of bandwidth they have and the network speed. So sometimes it'll be labeled, like this one says 100/10/100 base TX. That means that this network interface card is capable of speeds of 10 megabits per second or 100 megabits per second, depending on everything else in the network. The physical layer also involves the type of media that you're dealing with. And there's 3 types of media. There's copper wire, there's fiberglass, and there's wireless or air. So it's either copper, fiber, or air. Copper is relatively inexpensive. It's relatively easy to work with. If you went down to Fry's and you bought a 1,000-foot roll of Cat 5 or Cat 6 cable and some wire cutters and wire strippers and crimpers and a bunch of RJ45 connectors, then if you know what the pinout is, you could sit down and you could strip the wires and you could figure out how to terminate your own cable, how to build your own cable. It's not that difficult. It's relatively inexpensive. A 1,000-foot reel, last time I checked, you could buy a 1,000-foot reel of Cat 6A cable for about $95, so under $100 for 1,000 feet. It's relatively easy to work with, but it does have limited bandwidth. The bandwidth is limited by the capacitance of the cable. And as manufacturers of cable figure out better manufacturing techniques, they've been able to increase the bandwidth and make it faster cable. And that's why we have all these different categories of cable. You know, right now we typically use Cat 5, Cat 5e, Cat 6, or Cat 6a cable. Cat 5e is enhanced Cat 5 with better signal-to-noise ratio. It has a bandwidth of 350 megahertz. So you can use Cat 5e with 10 megabit per second networks, 100 megabit or 1,000 megabit per second networks. And 1,000 megabit is a gigabit, so you can use Cat 5e for gigabit networks. Cat 6 has a bandwidth of 250 megahertz. And Cat 6a is augmented Cat 6, and it has a plastic former to help reduce crosstalk. And if you look at how the differences in how Cat 5, Cat 6, and Cat 6a are constructed, the first thing you'll notice is the twist. You know, Cat 6a has a much tighter twist than Cat 6 or Cat 5e. And then also Cat 6a, if you look at the jacket, it has that mold to help keep the twist, because that's really important for reducing capacitance and keeping the bandwidth that it has. There's also Cat 7. Cat 7 is pretty rare in the United States. You see it more often in Europe, but in the United States, you don't often see Cat 7 cable. And part of the reason is that the Telecommunications Industry Association, the TIA, does not recognize Cat 7 because they say there's not enough improvement over Cat 6a, so they don't even recognize Cat 7. Now, Cat 8 came out in June of 2016. But again, Cat 8 is, I rarely see Cat 8. You rarely see Cat 8. It's more likely to be used in enterprise systems like banks and universities. Although I have seen some devices at lighting trade shows that are using Cat 8 or want you to use Cat 8, but it's very rare. There's unshielded twisted pair and shielded twisted pair. Yeah, Red?
If you go back to the other one, this has been a myth / question. You look at 5e at 350 megahertz versus 6 at 250 megahertz. There's an argument out there about 5e is still superior to 6 because of the bandwidth on it versus the 1,000 versus 10 gig. Can you address that since it's a...
Well, I don't know exactly, but here's what I believe, is that the way you designate 10 megabit per second Ethernet it's called 10 base T and 100 base TX. So the X stands for full duplex. So I believe, and there are people in the industry who know more about IT than I do, so somebody correct me if I'm wrong, but I believe with Cat 6 you use more than one pair, and so if you use 2 pairs, then that brings it up to 500 megahertz, which is better than 350.
The software that you can determine how to use that, and because of polarity cancellation or phase cancellation, if you want to think about it that way, that's why we use the twisted pair. And so yes, it can switch over, and so the 250 actually becomes the 506A.
Right. Yeah,
It is. But
that's what I thought.
A major misnomer out in the.
Oh, I see what you're saying. So what you're trying to correct a myth that it's better to use Cat 6e than to use 5e than to use Cat 6.
Correct.
Okay, and I'd go along with that. I think Cat 6 gives you more bandwidth than Cat 5e, even though it looks like that's not true, but it is because of the way it's used. Okay. Well, thanks for pointing that out. Yeah, Debbie.
Because of the interface with the computer,
Uh-huh.
I would suggest Cat 6.
What do you mean?
Because computers' speeds are going to flow better through Cat 6 ever than Cat 5.
Okay. Yeah, well, that's basically what so we're all in agreement then, right? Yeah. So the bottom line is you get better bandwidth with Cat 6 than with Cat 5e. Yeah, Ray?
Cat 5, just regular old Cat 5, you can't really find that so much anymore, right?
Exactly.
Yeah, no, that's true. If you go down to Fry's, you can buy a 1,000-foot roll of Cat 5e, but I think you'd have to buy it on the internet if you wanted a Cat 5. Yeah,
However,
Red.
The reason that it's pertinent is here is when you're running into a house wreck, for instance, Bailey Hutchinson Center in Dallas, their entire infrastructure was still run on 5e, or excuse me, on 5. And so a lot of times you'll go in with going into a house system where you're patching in.
Oh, yeah.
Getting into here, and all of your system is fine. You're testing good in the lab. You get it out to the show, and all of a sudden you get this bottleneck where you're having problems
Because they're using.
because you patched into the copper that's there, and they go, well, no, it's fiber. Well, no, it's fiber from where they did their rebuild to a patch panel or a media closet somewhere, and then all of that is old copper running through the system. So
Yeah, so in case you missed that, what Red is saying, and I completely agree, is that there's a lot of existing infrastructure that already uses Cat 5, because for the longest time, Cat 5 was it. Everybody used Cat 5. And so there's a lot of older buildings out there that have Cat 5. So if you go into a building and you try to patch into their infrastructure, don't be surprised if you have a bottleneck or you have issues because of the existing Cat 5 cable in the building. Now, there is unshielded twisted pair, and there's shielded twisted pair copper wire. Shielded twisted pair has a shield for added noise immunity, and if you are in a high noise environment, like maybe a video wall, or if there's lots of spinning machinery, then it's not a bad idea to use shielded twisted pair, which I believe is Cat 6 or Cat 6A. Unshielded twisted pair in a lot of applications work just fine. I've never had issues with Cat 5e. But certain times you might want to use shielded twisted pair. There's also a difference between normal Ethernet cable and plenum rated cable. If you're doing a permanent installation and you're running the cable in a fresh air plenum, a plenum is a return vent for the HVAC. Then by code, fire regulations say you have to use plenum rated cable for that purpose. And the reason is that in the event of a fire, usually when people die, it's not because they get burned to death, but because they asphyxiate. They inhale smoke and they can't breathe. And plenum rated cable is Teflon coated. That's a fire retardant. So if there's a fire, then it gives them more time before it starts releasing toxins, and it'll get into the air conditioning system. So it gives people more time to get out of the building. When you're running your Ethernet cable, try to avoid sources of electromagnetic interference. Things like LED video walls, fluorescent lights. You know, envision a big cloud of electromagnetic interference around fluorescent lights and LED walls and LED fixtures. So it says you want to try to leave at least 3 feet of space between a cable and a source of electromagnetic interference. And now the maximum allowable cable run for Ethernet technically is 100 meters, which is 328 feet. But I've talked to lots and lots of technicians who tell me that the number one issue with Ethernet is that people try to run their cables too long. So lots of experienced techs that I trust will say you want to limit it to between 200 and 250 feet. If you try to go more than 250 feet, you're almost guaranteed to have problems. If you run it less than 250 feet, you're going to have much better luck, much better success. So even though technically you're supposed to be able to run at 328 feet, don't believe that. The real number in practical terms for a good, solid, stable connection is between 200 and 250 feet. There's two different ways. If you're building your own Ethernet cable, there's two different ways to terminate it. One of these ways is used by AT&T. The other is more common. And it honestly doesn't matter which one you use as long as it's the same on both ends. Now, this is what you and I would call an RJ45 connector. Technically, it's an 8-pin, 8-conductor connector, 8PHC. But either way, this is fine for permanent installations, home applications, office applications. It's terrible for portable applications. Why? Because this little tab right here is the only thing that holds it in place, and it always gets broken on the very first loadout. I've done lots of shows where after the first loadout, every stop we have to plug it in, gaff tape it, and it's not very good. Yes, Raphael?
Real quick, going back to the runs of 200 and 250 feet, that doesn't matter if you're using Cat 5 or Cat 6. So
Raphael's question is where it says the recommended maximum run of cable is between 200 and 250 feet. His question is, does it matter if it's Cat 5, Cat 5e, Cat 6, or Cat 6a? I think it does have an influence, but the numbers that I've read are strictly the technical specifications. So I don't know. I can't tell you what the standard practice in our world is, except that I believe you should not, regardless of the type of cable, it should not be more than 250 feet. Okay? Now, so that's an RJ40, what you and I call an RJ45. RJ45 really is the jack itself, but technically that's an 8PHC connector that's connected to an RJ45 jack. But we all refer to it as an RJ45. There's no harm in calling it an RJ45. Everybody knows what you're talking about. Now, this is a ruggedized Ethernet connector, which is much better for portable applications because it has an aluminum shell that protects that plastic tab right there. So this particular brand, there's different brands. This one is a Neutrik Ethercon, but there's a few other brands out there as well. The thing you have to look out for in these connectors is that sometimes that plastic APHC connector gets pushed back into the shell, and then when you plug it in, it doesn't make good contact, and you start to have problems.
Buy the Elation version, it'll be okay.
Buy the Elation version, and it'll be fine. The sun will come out, the birds will sing, it'll all be good.
And if not, it will be erased smoothly.
Now, this is a picture of the panel on a fixture that has an Ethernet connector. If you see a lighting fixture that has an Ethernet connector, then that means if it has one Ethernet connector, that means it has a built-in gateway. A gateway is a protocol converter, and it converts between some Ethernet-based protocol like ArtNet or streaming ACN, and it converts it to DMX. So if you turn on the gateway in the fixture, then you're allowed to run some Ethernet-based protocol, ArtNet or streaming ACN, directly to the fixture, and then you can come out of it with DMX. So the advantage is you don't need an external gateway. And also some fixtures are so bandwidth hungry, they take so many parameters that if you want to run it DMX, you can, but it'll take half of a universe. So by having Ethernet, that helps ease that demand on the DMX. Now, if you look at a fixture, and it has two Ethernet connectors on it, one will be labeled input, one is labeled output. That's an example of a fixture that has a two-port switch built into it. You know, a switch is how you build a network. So this is a switch. Come on out of there. This is a 5-port switch. If I had a 2-port switch and I put it inside of that fixture. Now what that allows me to do is I can run a cable from the console to the input of this port. Then I can take the output and run it to another fixture. And then if I wanted to daisy chain that, I can run it to another fixture and so on. Now, if you have fixtures like that with 2 Ethernet ports, you really have to be careful, because here's what can happen. Suppose, for example, you set up the console to output ArtNet, and you have a fixture that has a 2-port switch in it. What happens is that the console will send an Ethernet packet to the fixture, to the switch. The switch has to get that data, and it has to look at the packet. And in the header, it'll tell the receiver what kind of data it is. Is it DMX? Is it RDM? What is it? And also, it'll tell you the destination address. So if the data is intended for another fixture, then it's going to output it on the output port and send it to the next fixture. The next fixture will get it, open the packet, read it, figure out what kind of data it is, where it's supposed to go, and if it's intended for another fixture, then it'll output it to the next one, and the next one, and the next one. The problem is that every time a switch has to read a packet, it takes time. It's latency. It's delay. And so by the time this fixture reads it, and then that one, and that one, and that one, a relatively high amount of time has lapsed. Now, ArtNet uses a certain packets. The way ArtNet works is ArtNet continually polls every fixture on the network to see if it's still active, to see if it's still connected to the network. It sends out an ART poll packet, and it allows 3 seconds for a reply from that fixture. If it doesn't receive a reply within 3 seconds, then it assumes that that fixture has been taken off the line. So if you have these fixtures with the 2-port switch and you try to daisy chain too many fixtures, then there's not enough time for the ART poll packet to return back to the controller, and the system stops working. So when you have those kinds of fixtures with a 2-port switch built in, don't try to daisy chain 16 of them. It's not going to work well. In my experience, you can daisy chain up to about 4 fixtures and no more than about 4. Yeah, Ray?
But ArtNet's so fast, DMX is so slow, shouldn't really be an issue, right?
Yeah, so Ray's comment is that ArtNet is fast, DMX is slow, so why is it an issue? The answer is that the network adds latency. So even though the speed of the network is based on the baud rate, we're talking about the throughput of the network. So if there's a lot of traffic, or if there's a lot of devices, then if you're that's called the cascade. If you're cascading too many switches, then you're adding latency, you're adding delay, you're slowing it down, even though ArtNet, even though Ethernet and ArtNet are fast protocols, it's the network that's congesting it and slowing it down. Does that make sense? Now, fiber optic cable is great because it's got huge amounts of bandwidth. The way fiber works is it's actually made of glass, and there's a LED transmitter on one end and a photoreceptor on the other. So the LED is flashing at a very, very high rate of speed, and it's transmitting data in the form of light pulses. The advantage is that it's completely immune to electromagnetic interference, whereas an electronic signal, if you run it near a fluorescent light or an LED wall, then you could get interference. But fiber optic transmission is completely immune to electromagnetic interference. It doesn't mess with it at all. It is more expensive and it is fragile. If you bend fiber too far, it has a maximum bend radius. If you bend it too far, it'll snap and break. Although, having said that, last January, I was at NAMM in Anaheim, and there's a company that had some fiber optic cable, and they were actually kinking it. They were squeezing it and kinking it, and it didn't break. And they were passing a signal through it. Now, when you kink it, it's kind of like a hose. It slows down the data rate that goes through it, the throughput, but the data still gets through, and it doesn't break the fiber. So they are coming up with ways to make fiber more durable, which is very impressive. But normally, fiber has a maximum bend radius, and if you step on it, it'll break, If you run a forklift over it, it'll break. Sometimes if you look at it wrong, it'll break. So you have to be careful with fiber. Now, it used to be that terminating fiber was very arduous, and it was kind of difficult to do. You used to have to cleave it or cut it and then polish it before you terminate it. Now they have better tools. They have cleaving tools like this right here, although they're kind of expensive. I think that one right there cost about $800. And then they also have machines that will terminate fiber automatically, but you have to be trained on how these run and how they work. And even if you're manually terminating fiber, training's important, because there are safety issues involved. When you cleave fiber, it can develop splinters, and you don't want to get a glass splinter in your eye or on your hands, on your fingers. So they have various classes that will train people how to be fiber techs. And also part of that is, after you terminate it, you have to test it to make sure you have a good termination, because if you have a weak termination point, then you're going to, the signal is going to be attenuated. So they'll teach you how to terminate it, how to test it, and how to measure the attenuation in decibels. There's certain machines like this one, like these ones, that will generate a signal and receive a signal, and it'll tell you how much the signal strength has dropped, and that's how you'll know whether or not you have a good connection. There's lots of different fiber connector types, and at first I started trying to list them all, and I quickly realized that there are far too many to list. But the bottom line is that the way you generate a fiber signal is you have a switch. Now this switch right here, for example, only has copper ports, only has RJ45 ports. But there are some switches that have fiber ports as well, like this one right here. And so if you see something with a fiber port, then that will tell you what kind of connector you need. So this particular one uses FiberCon, which is a Neutrik connector. And so if you're going to use this switch, you need fiber optic cable with FiberCon connectors on it. They also make armored cable, or it's called tactical fiber. Tactical fiber came out of the military, and it is sheathed in a metal armor, and so it's actually designed where tanks can run over it, and it won't break the fiber in it. You know, it's heavy, it's thick, it's expensive, but in certain applications, what it gives you is the ability to send a signal for a mile and a half, very, very long distances. So if you're doing a big show, if you're doing the halftime show at the Super Bowl, if you're doing the Olympics opening ceremonies, you know, then that might be what you would use for those types of applications. Yeah, Raphael?
Quick question. Do you see the industry moving more towards fiber?
Yeah, that's a great question. So Raphael's question is the industry moving more towards fiber? And the answer is absolutely yes. About, I want to say 2 or 3 years ago, I was working on a show in New Orleans, and I was on the lighting crew. The video crew was set up backstage, and they had their video world there, and they had a whole bunch of media servers. I think they were Hypnotizer media servers. And I was chatting with the video director, and he told me that he had just come off of a 2-year tour with Justin Timberlake. And this was his very first show since he had come off of that tour. When he left with Justin, you know, when you design a tour, you're going to design a system, and you carry that same equipment for 2 years. And then when he got off the tour, when he went back to the shop, he was surprised to learn that everything had changed in the video world. And the biggest change was that no longer were they using fiber, or no longer were they using copper to distribute video signal, but they were using fiber. And you see that a lot. So in the video world, most of the time now, they're distributing their signal with fiber optic cable, and audio is going through the same transition. If you think about the way analog audio used to be transmitted, you had a mixing console with multiple channels, 96 channels or whatever, 148 channels, whatever, and you're sending that to the amplifiers which live by the stage. And so you used to have big, thick audio snakes that had multiple pairs of conductors in it. That's being replaced by a single Cat5 cable, in a lot of instances fiber instead of copper. In our world, For big shows, you often see a fiber backbone. So they have switches that convert copper to fiber. They ring it around big areas, and then you have switches that convert it back to copper. And then there are consoles that have fiber ports as well, and that was the PRG console. The Artisan has a built-in fiber port. So yeah, we are seeing more use of fiber in our industry, and there's a growing demand for fiber optic technicians as well. I was told that during the London Olympics, now remember, at the London Olympics, that's where they had a fiber backbone around the stadium, and they built the network into every single seat in the stadium. That's 70,500 nodes in that network. And I was told they had a crew of 6 or 8 full-time fiber techs who for 3 or 4 months, all they did was install fiber and repair broken fiber and test it. It's a full-time job for several months. So yes, there's a growing demand for fiber techs. Let's see what time it is. Okay, so yesterday we talked a lot about wireless DMX and Wi-Fi. So for some of you who were here yesterday, this information is going to be redundant. If you weren't here yesterday, there's a couple of things that there are a couple of things about wireless DMX that we want to cover. And here's the thing about wireless DMX is that it's becoming more reliable. It's becoming more accessible, and the prices are dropping as well. So wireless DMX is very similar to Wi-Fi, except there are some advantages using wireless DMX over Wi-Fi. And the 3 main advantages are that commercial Wi-Fi is a fixed frequency transmission, whereas most wireless DMX uses adaptive frequency hopping spread spectrum technology, which means that instead of just transmitting on a single channel, it's constantly changing the channel that it's transmitting on 1,000 times per second. So that way you have a much better chance of getting the signal through. And here's one thing too that I didn't mention yesterday is that some wireless DMX sends redundant packets. So they'll send 2 DMX packets for every 1 packet that the console is sending out. So that way if 1 packet doesn't make it, if it gets corrupted or lost or gets blocked, hopefully the other packet will get through. Also, the signal power for wireless DMX is typically much stronger than commercial Wi-Fi. And thirdly, they are constantly coming up with new schemes to get around problems associated with interference. So for example, Red, what's the name of the Elation wireless it has that uses channel 14? eFly. So Elation has a wireless DMX system called eFly that uses a channel in the 2.4 gigahertz spectrum, channel 14, that is normally not used. It's not allowed, nobody's allowed to use, but because they got variants, they got special permission, then they can go ahead and use channel 14. So if you have a lot of problems with interference, then you can try a wireless DMX solution that uses channel 14 to get around that problem with interference. Okay, so that's the eFly transmitter. In the 2.4 gigahertz range, sorry, that's not what I meant to say. In commercial Wi-Fi, there's different types of Wi-Fi. These have been developed over time. The first one is 802.11a that uses the 5 gigahertz range. Now 5 gigahertz line of sight can go about 150 feet. Later on they came out with 802.11b, which works in the 2.4 gigahertz band, which by the way is called the Industry Science Medicine band. It can go up to 300 feet. 802.11g uses the 2.4 gigahertz band, but it's got more bandwidth. And the 802.11n uses the 5 gigahertz band with more bandwidth. And then AC has, under perfect conditions, a gigabit of bandwidth on the 5 gigahertz. And most of these are dual band routers, so they'll, in addition to running on the 5 gigahertz band, they also have a 2.4 gigahertz signal as well. AD is another protocol that they're developing as well. So this is the 2.4 gigahertz spectrum, 14 channels in it. And yesterday I learned there's actually channel 0, which I did not know. But so I guess there's 15 channels in 2.4 gigahertz. But in North America, we're only allowed to use 1 through 11. Now, each channel spills over in two channels on either side of it. So channel 1 will spill all the way to channel 3. Channel 6 goes from channel 4 to channel 8. And channel 11 goes from channel 9 to 13. But notice 14 is untouched. So that's why having the ability to transmit on channel 14 is a great way to get around the problem of interference if that's your issue. And this just illustrates the bandwidth for one Wi-Fi channel. So you're covering, one channel covers actually 5 channels, okay? So this illustrates the difference between the 2.4 gigahertz band and the 5 gigahertz band. So in the 2.4 gigahertz band, there are only 3 channels that don't overlap with each other. Those channels are channel 1, channel 6, and channel 11. And then in the 5 gigahertz band, there's a whole different channel scheme there as well. Now, the further you're trying to transmit, the less throughput you'll get. So if you're trying to get the best throughput, then you want to try to limit the distance that you are transmitting using Wi-Fi. When you're setting up your wireless system, then you want to try to get line of sight. And the best way to do that is to elevate the transmitter. So rather than mount the transmitter on the ground, it's best to put it up high in the air, and some manufacturers say mount it 8 feet up in the air for best results. Now, the obstacles will block the signal. Think of Wi-Fi as another form of light. You know, light will cast a shadow, and Wi-Fi can cast a shadow too. So things that block and absorb the energy from the signal will cast Wi-Fi shadows. And anything that has a lot of water in it will absorb more of the energy than things that don't. So things like plants, trees, people that have high water content will block the signal more. Electromagnetic interference can also interfere with wireless communication. Things like lightning, LED walls, fluorescent lights, those can cause problems with wireless as well. So this kind of illustrates how a transmitter is sending out a signal, and it behaves very much like light does. So the further you're trying to go, the more it slows down the signal. Signals can also reflect off of metal and cause signal reflections that can interfere with the transmission of wireless. You can use signal repeaters. There are, like for example, my wireless router, if I had 2 of them, I can put one in bridge mode, which will repeat the signal, but that also takes time to rebroadcast it, so it adds latency and slows down and minimizes the bandwidth.